So this is our last class, which makes me kind of sad. But also I'm excited that we got through the whole quarter. And I have a different setup today because I was in meetings here at UCR all day, so I didn't have a chance to get home. So unfortunately, I have a hard time seeing your chats while I see my screen. So forgive me if I don't get to your questions right away. I'll try to do my best. But right, so let me just get started. And also, like I don't get to see my entire screen. Anyways, I'll try to do my best here. So today is the last day to complete iEval. So again, if you have a chance, please leave me some feedback there. Also, today is the last day that you have discussion sections. I think there's only 2 left, so everybody else should be done with them. There is a video with answers to homework 8 that is posted on iLearn that you guys can access. And finally, I will be posting homework number 10 tonight. There is no quiz for that. There's no discussion sections, but it'll be, to help you to study for the final. And speaking of the final, I will give a review for the final this Sunday at 5 p.m. So it'll be the same link than the one that you're using right now. And what I'll do with that time is I will go over the questions for homework number 10 as if you had a discussion section on that. Then I will give you a brief review of the main topics. I'm not going to go, one by one of the little ones, but sort of the big topics, the things that are sure to be on the final. I will give you a reminder. And then after that, I will just open it for questions. So then I will just answer your questions. I will record it and post it. So of course you can watch it later, but I can only answer your questions if you come. So that's it. It'll be nice to have one more chance to have interaction. And then of course I will see you in person on Wednesday at the test. So the final will be in person, Wednesday, December 8th, 3 to 6 p.m. at the University Lecture Hall. Please bring a Scantron. Form 289 Part L. By the way, there's an F before the 289, so some people have asked me about that. It is the same, F289 Part L. It's the red one, like the one that I'm showing here. Try to get the one that actually says Scantron here, not the ones that are compatible with. It's okay if you can't find anything other than the compatible ones, then that's fine. But if at all possible, try to get this type of Scantron because they have fewer problems with the machines. All right, so that's it for that. And today we're going to talk about the Big Bang. So the very, very beginning of the universe. And we only have, 45 minutes to talk about it. So I'm going to be very brief. And again, if you're interested in this, you can take other classes like Physics 37 or Physics 5, which go into a lot of detail about this. Anyways, the Big Bang. We talked about how today the universe is expanding. And the universe has been expanding for a long time. And we saw that in the past, it was expanding not as fast. And now it is expanding faster. And this is something that we were able to do by measuring the rate of expansion in the past versus now. But the point is, it has been expanding from the beginning. And which means, if I told you last time or 2 times ago that if we sort of play the tape backwards, right? If we go to the past, we can imagine how everything was close together. The universe was very dense until the point where everything is together in one singularity. And you can imagine how the universe would have been very hot and very dense. We've talked about the opposite. For example, in a red giant, when a star sort of expands incredibly, drastically, the outer layers become cooler. So this is the opposite. You're getting the entire universe to contract in the past and be very, very small. So it had to be very, very hot. And so So the Big Bang presumes this. The Big Bang presumes that everything that you see today, galaxies, planets, everything began as an incredibly hot, dense, tiny collection of matter and radiation. It presumes that space and time had a beginning. What the Big Bang theory is just a theory, a model that describes how that expansion took place to go from the tiny little point at the beginning of time and space to what we see today. So how did things change? How did physics change? How did the properties of matter change as things expanded and cooled down? Now, the ideas about the absolute earliest moments of the Big Bang necessarily have to be speculative, because as we will see in a few slides, we don't yet have physics. We haven't worked out the details of theories that would describe the universe when it had very extreme conditions. And by extreme, I mean the entire universe was in extraordinarily small spaces, right? And it was extraordinarily high temperature, which, by the way, I will be saying high temperature, high energy. You can almost equate those two. So very high energies, very high temperature, and we don't have the physics that describe that. And I'll tell you more about that a little later on. As the universe expanded and the temperature dropped, and the conditions of the universe became a little more like what we have today in our universe, then the evidence becomes stronger, and then we can actually work out models and theories that are testable, that we can actually observe and see. So for the rest of the class, we're going to talk about some of the major eras or time periods of this story of creation, right? So by eras, so it's time periods, kind of like when you study the Earth and you talk about the Paleozoic and the Mesozoic, you know, like different eras of the Earth when sort of important events happen on Earth. We have the same in the study of cosmology, the study of the Big Bang. We have the same for the universe. So there are different eras. In your textbook, you have this, this graph, which is showing you on the x-axis time elapsed since the Big Bang. So we start here at the Big Bang, or almost at the Big Bang, and then it goes all the way down to present day. On the y-axis, you have temperature, and you can also think of energy, like the types of energies that were available in the universe. And so you can see how the temperature has been dropping steadily as the universe has been expanding. You might notice that the units are in logarithmic scale, which all that tells you, the fact that it's logarithmic, it means that it's dropping very quickly, right? So even though it looks linear, it actually is logarithmic or exponential, as many times we say. So in your textbook, it talks about some of the most important things that happens as the temperature drops. And so we're going to go through some of them. But since we only have one class and we have to go through things very quickly, this is sort of a summary of what we're going to talk about today. We're going to talk about what happened in the very beginning of the Big Bang of the universe, what happened during the first tiny fraction of a second, a period that is called inflation. It's an event that happened and that made the universe grow very quickly. And then something that happened at 380,000 years after the Big Bang, and then all the way to today. But I'll get back to this slide at the very end, and then I'll summarize the different things that we talked about. All right, so first of all, the very beginning, the absolute first tiny fraction of a second. So this is what we call the Planck era. So the Planck era goes from the beginning of the universe to a fraction of a second that is tiny. It's a 10 to the minus 43. What does that mean? So if you were to draw it on a board, it would be 0 point, and then you would do 42 zeros and then a 1. So 10 to the minus 43 is the fraction of a second that is called the Planck era. The significance of this time is that we actually don't know what happened during that time. So here's the thing. In the universe, we have two sets of theories that are not compatible with each other. We have general relativity. We talked about this before in class. We talked about how general relativity describes the universe as a whole, the very large. It describes gravity. So if you remember when we talked about how gravity caused a curvature of the universe, and the reason why the Earth is going around the sun is because the sun is curving the space around it, and just black holes, all of these things are described by general relativity. General relativity is the theory of the very big. And then there's a different thing that we didn't cover in class because it's a different class, right? But it is the theory of the very small. And the theory of the very small is called quantum mechanics. This is what describes how atoms behave, how subatomic particles like protons and neutrons, and then like even smaller ones like quarks. It describes how the universe also behaves, but at very, very tiny scales. And those two are not compatible with each other. And I have a video to illustrate this a little better. But normally this is fine, because if you're talking about planets and galaxies and clusters of galaxies, you just use general relativity. You don't have to worry about the tiny things because everything is so big. And usually you don't worry about gravity when you're dealing with atoms and when you're dealing with quarks and these tiny little things. They're like two different worlds and you don't have to put them together. But when the universe began, you had the entire universe in a very tiny, tiny space, which means you have to combine these two together because the very big was very small at the time. And we don't know how to do that. There's a lot of people working on this, don't get me wrong, but they still haven't come up with a way to put together general relativity and quantum mechanics. So I have a video that it's kind of old, but it's pretty fun. I like the way that they show these two theories. So let me go ahead and play that.
But before we can find that theory, we need to take a fantastic journey to see why the two sets of laws we have conflict with each other. And the first stop on this strange trip is the realm of very large objects. To describe the universe on large scales, we use one set of laws, Einstein's general theory of relativity, and that's a theory of how gravity works. General relativity pictures space as sort of like a trampoline, a smooth fabric that heavy objects like stars and planets can warp and stretch. Now, according to the theory, these warps and curves create what we feel as gravity. That is, the gravitational pull that keeps the Earth in orbit around the Sun is really nothing more than our planet following the curves and contours that the Sun creates in the spatial fabric. But the smooth, gently curving image of space predicted by the laws of general relativity is not the whole story. To understand the universe on extremely small scales, we have to use our other set of laws, quantum mechanics. And as we'll see, quantum mechanics paints a picture of space so drastically different from general relativity that you'd think they were describing two completely separate universes. To see the conflict between general relativity and quantum mechanics, we need to shrink way, way, way down in size. And as we leave the world of large objects behind and approach the microscopic realm, the familiar picture of space, in which everything behaves predictably, begins to be replaced by a world with a structure that is far less certain. And if we keep shrinking, getting billions and billions of times smaller than even the tiniest bits of matter, atoms and the tiny particles inside of them, the laws of the very small, quantum mechanics, say that the fabric of space becomes bumpy and chaotic. Eventually, we reach a world so turbulent that it defies common sense. Down here, space and time are so twisted and distorted that the conventional ideas of left and right, up and down, even before and after, break down. There's no way to tell for certain that I'm here, or both places at once. Or maybe I arrived here before I arrived here. In the quantum world, you just can't pin everything down. It's an inherently wild and frenetic place.
The laws in the quantum world are very different from the laws that we are used to. And is that surprising? Why should the world of the very small at an atomic level, why should that world obey the same kind of rules and laws that we are used to in our world with apples and oranges and walking around on the street? Why would that world behave the same way?
The fluctuating, jittery picture of space and time predicted by quantum mechanics is in direct conflict with the smooth, orderly, geometric model of space and time described by general relativity.
All right, so I like this video a lot because I just like I like how contrasting those worlds are. And again, with quantum mechanics, all you can ever get is a probability. You can never pin down like what exactly the momentum or this position or the energy of something is. There's always a probability, and that's why, you know, he says that there's no conventional before and after, and so on. So anyways, hopefully this gives you an idea of how these two theories are so different from each other, and there is no thing to put them together. You may have heard of string theory. If you ever watched that long-running show, The Big Bang Theory, it's called, with Sheldon. Sheldon was studying string theory, and string theory is something that actually attempts to put quantum mechanics and general relativity together. But so far they haven't been, I mean, this video is actually from string theory, and they'll tell you that they're successful. But the problem is you cannot test the theory. And if you cannot test it, then, you know, in my opinion, it's still it's more like philosophy, right? It's good ideas, but we need to be able to test them. And we still don't have that. So until we have a theory that links quantum mechanics and general relativity, we don't actually know what happened during the Planck era. And it's a tiny, tiny fraction of a second, right, where we don't know, but it's still kind of significant. We really don't know. Can a singularity be seen as an example of the quantum realm? Yeah, so that's a question in the chat. So that is the issue, right? That a singularity has the scale of something that needs to be treated as quantum mechanics. But the problem is, it's in this case, in the case of the Big Bang, it contains the entire universe, and the entire universe is described by general relativity. So how do you put those two together? So that's the problem with the Planck era. So we're going to skip to the point where the universe grows enough and the temperature drops enough to a point where we can actually start to apply the physics that we have today and try to model what and figure out what was happening in the very early universe. So one thing that we know is that the forces of nature, behave differently at different temperatures. This is something we know because we have tested it. And so we know that in the very early universe, when it was very hot, the forces that we know today operated differently. So let me give you a brief summary of the forces that we have. So today in the universe, we have 4 different forces. And we've been talking a lot about one of them. In this class, we talked almost every single lecture, we talked about gravity. Gravity is it's the weakest of all the forces, but it is what dominates the action at very large scales. So you know a lot about gravity, I hope, by now. Electromagnetism, this is something that you're very familiar with because these are the forces that, dominate chemical and biological reactions. This is, when you turn on your lights or even with the sun, when we talked about the magnetic fields in the sun and light is an electromagnetic wave. So electromagnetism, that's a force that we're pretty familiar with. I introduced the strong force a while ago when we talked about fusion. So I told you strong force, it's the strongest of all 4. And the strong force is what keeps nuclei together. It's what keeps 2 protons from repelling each other. But the thing with the strong force is that it only acts over very small distances. And so even though it is a lot stronger than gravity, gravity ends up dominating at large distances. The one force we haven't talked about is the weak force. And this is a little bit more difficult to describe because we don't use it in day-to-day life. But the weak force is what mediates nuclear reactions, such as fusion. So I did tell you at some point you need 4 protons in order to make 1 helium. But 1 helium doesn't have 4 protons. A helium has 2 protons and 2 neutrons. So the force that turns the protons into neutrons, that's the weak force. And so anyways, those are the 4 forces that we have today. I think I have a video too yeah, I do. So this video will just tell you a little more about the weak force and then how these 2 forces go together.
By the 1930s, Einstein's quest for unification was floundering, while quantum mechanics was unlocking the secrets of the atom. Scientists found that gravity and electromagnetism are not the only forces ruling the universe. Probing the structure of the atom, they discovered 2 more forces. One, dubbed the strong nuclear force, acts like a superglue, holding the nucleus of every atom together, binding protons to neutrons. And the other, called the weak nuclear force, allows neutrons to turn into protons, giving off radiation in the process. At the quantum level, the force we're most familiar with, gravity, was completely overshadowed by electromagnetism and these 2 new forces. Now, the strong and weak forces may seem obscure, but in one sense at least, we're all very much aware of their power. At 5:29 on the morning of July 16, 1945, that power was revealed by an act that would change the course of history. In the middle of the desert in New Mexico, at the top of a steel tower, about 100 feet above the top of this monument, the first atomic bomb was detonated. It was only about 5 feet across, but that bomb packed a punch equivalent to about 20,000 tons of TNT. With that powerful explosion, scientists unleashed the strong nuclear force, the force that keeps neutrons and protons tightly glued together inside the nucleus of an atom. By breaking the bonds of that glue and splitting the atom apart, vast, truly unbelievable amounts of destructive energy were released. We can still detect remnants of that explosion through the other nuclear force, the weak nuclear force, because it's responsible for radioactivity. And today, more than 50 years later, the radiation levels around here are still about 10 times higher than normal. So, although in comparison to electromagnetism and gravity, the nuclear forces act over very small scales, their impact on everyday life is every bit as profound. But what about gravity? Einstein's general relativity, where does that fit in at the quantum level? Quantum mechanics tells us how all of nature's forces work in the microscopic realm except for the force of gravity. Absolutely no one could figure out how gravity operates when you get down to the size of atoms and subatomic particles. That is, no one could figure out how to put general relativity and quantum mechanics together into one package.
All right. So I want you to keep that in mind, the whole video, but there's a part where he talks about how when the atom was split, the strong force was unleashed. And just think about what the atomic bomb did with something so small, 5 meters across, I think he said. And it unleashes incredibly destructive, incredible, huge amounts of force. So keep that in mind, and we'll get to that right now. But what I was telling you was these 4 forces behave differently at different temperatures. And if you think about the universe, we've been talking about how the universe started with the Big Bang on the left of this graph here to today on the right. And so besides time passing from left to right, the temperature is also dropping. So higher temperature, hotter to cooler temperatures of the universe as a whole. And again, today we have 4 separate forces, but it appears at higher temperatures, some of these forces actually merge together. And I'll get back to this graph in a second. But so we have the forces, the 4 forces, and the universe is cooling down, right? And so they separate, but let me go backwards. So today we have the 4 forces, but we can have experiments at accelerators. You might have heard about the physics accelerators, particle accelerators, where they can recreate very extreme conditions, very high energies or very high temperatures, and they can figure out what happens to the forces. Turns out that the weak force and the electromagnetic force, when you increase the energies or the temperatures to much higher as they were in the past, they actually merge and they become one force. So instead of being the weak and the electromagnetic, they become the electroweak. And this is something that has been tested. They tested all over and over again at the lab. Now, that's as far as we can test. We do not have labs that can get to even higher energies. But it is thought, at least it works with math, that if the energies were much higher than what we can achieve in the lab, then 3 of the forces would unify. And so it would be the weak, the electromagnetic, and the strong forces. So all 3 of them, or the weak and the electroweak. And because the theory that predicts this is called the Grand Unified Theory, GUT, this is called the GUT force, right? The GUT force. So where you get three forces merged into one. So electroweak and strong, it would be this. And then this is a lot more speculative. But we think that in the very, very early universe, in the very early universe, only two forces operated, and that would be gravity and this triple force, the GUT force. And so, and then, you know, at the very, very beginning, maybe all of them merge, but we don't really know. That would be at the Planck era. But at least after the Planck era, the gravity sort of separates from the GUT force. And so we start with that, right? I'll get back to this. So in the beginning, we would have all forces being equally strong. Maybe they were unified, we're not so sure. But after the Planck era, we get gravity separates, and then we have this GUT force. Somebody was asking me what is the era called? Well, they name it the GUT era because of the GUT force. But as the universe continues to cool down, and we're a little more sure about this, although it's still not fully it's not fully proven, if you will. So as the universe continues to expand and cool down, the strong force separates. And that's why I wanted you to remember about that video. What happens when the strong force is unleashed? What happens is that it releases an enormous amount of energy. And we think that that energy that was released, you know, instead of just exploding and causing destruction, what it actually did is it was injected into the universe, and that enormous amount of energy caused inflation. So that's why I wanted to talk about the forces, right? Because the universe, it's hard to explain why the universe is as big as it is right now. And by big, I mean the distances between galaxies, right? Any typical distance in the universe is very big today. And so how did we get from the singularity to this? And what we believe, and again, this is still in, you know, still hypotheses, but what we believe is that the strong force, because the universe, the temperature of the universe is going down, the strong force gets separated from the electroweak, right? It was the GUT force when all three were together. The strong force becomes separate from the electroweak, and that amount of energy gets injected into the universe, and then the universe expands dramatically. And then eventually, you know, the electromagnetic and the weak will also separate, but nothing too amazing happens there. So we have, you've probably seen this, it's behind me in my background. You've seen a lot of, if you Google Big Bang, you will get something that looks like this. And what this is representing is how the universe changes over time from left to right, from hot to cool, and also how it sort of grows. And you have the Big Bang, which again, we don't know what happened. And then you get this period that is called inflation. And so inflation would be this sudden and dramatic expansion of the universe when the strong force separated from the electroweak and from the electroweak force, and that amount of energy that came from the strong force goes into inflating, you know, like a balloon, inflating the universe and making it much bigger. So then after that, the universe sort of grows at a more reasonable rate. But during inflation, it must have grown very, very fast. If you notice the units, it's still a very tiny fraction of a second. It's still not even 1 second after the Big Bang, and all of this has already happened. All right, so inflation ends, and then after that, the universe is still very hot. It's, you know, during the first microsecond, and there's other eras that I'm not going to talk about, the electroweak era, the proton era. So I'm not going to talk about those just because we don't have time, but let me skip ahead a little bit to the first few minutes. And this is when the universe has cooled down enough that protons can actually exist. I mean, before that, it's just like radiation in the universe, but now we can actually have protons. And we call this the era of nucleosynthesis because we have protons which you can use for fusion, and the universe is hot enough that those protons will be moving very fast and they can collide with each other and they can actually fuse to form other elements. So since the universe at the beginning, when protons can form, they're just protons. So what do we call protons by themselves? Well, they're hydrogen nuclei. So the entire universe at this point is hydrogen. And this is why hydrogen today is the most abundant element, because at the very beginning, and because it's the simplest, right? Protons, just protons by themselves, that's hydrogen nuclei. But the universe in the first few minutes, it's super hot. And then it is a lot like if it was the interior of a star. It's very hot, over 10 million degrees Kelvin. And so protons can actually fuse and they can form helium. So this should be reminding you of the lectures when we were talking about the center of the sun, right? The core of the sun, where hydrogen gets fused into helium. So the entire universe, you can think of it as being the interior of a star, which is kind of crazy to think about. So the universe is busy at this point, at this era of nucleosynthesis, where hydrogen is becoming helium. But the universe continues to expand and it continues to cool down. So at some point, the universe will be under the 10 million degree Kelvin threshold. And so at that point, it stops fusing. And when it stops, the universe is 75% hydrogen and 25% helium. So a lot of helium was formed at this time. And this is, again, this is why the universe today is mostly hydrogen and helium. The universe continues to cool down. So there's not going to be any more fusion in the universe. So from now on, from this point on, the only place where you ever get fusion is inside of stars. But in the very early universe, the first few minutes of the universe was able to fuse hydrogen into helium, and we ended up with hydrogen and helium. Again, after this, you need stars in order to create heavier elements. All right, so the universe continues to drop. Oh, and I see that I'm almost out of time. All right, I'll try to do this fast. So the universe keeps dropping. The temperature keeps dropping. And the next sort of important or momentous thing that happens is when the temperature of the universe drops below 3000 degrees Kelvin. What's important about this temperature is that at that point, protons can actually combine with electrons to make atoms. Before that, when the universe is hotter, you have like a soup of protons and a soup of electrons, right? And everything is going around. So actually have it on the next slide. So before it drops to 3000 degrees Kelvin, you have a bunch of protons, a bunch of electrons. And the problem is when a photon, when a particle of light tries to get through them, it can't. It gets bounced around, just the way that I told you that it happened in the radiation zone of our sun. So remember that it took like 1 million years for a photon to get out of the sun? Same thing is happening in the entire universe. The entire universe is a bunch of electrons and protons, and light cannot travel in a straight line. But when the temperature drops to 3000 degrees Kelvin, protons can trap electrons And then they're sort of more confined, right? They're closer together. And so then there's a lot of space in between them, and photons can travel freely through the atoms. So we call this recombination. It's a bad name. It should be called combination because it's the first time that they combine protons and electrons, but oh well, it has the name recombination. So recombination is this moment when the universe goes from being very hot, it drops to 3000 degrees Kelvin, the temperature. And so atoms can form, hydrogen atoms can form, the universe becomes transparent. What do I mean by transparent? It means light can actually travel freely, much in the same way that in the sun, as photons are trying to escape the sun, they can't, they get bounced around. But then finally, when you get to the photosphere of the sun, then light can actually travel in straight lines. So here, it's a matter of time. The entire universe is too hot, but photons get bounced around. And then finally, the temperature drops to 3000 Kelvin. And finally, light can travel in straight lines. This happens at 380,000 years after the Big Bang, one of the few numbers that I'm asking you to remember. So, 380,000 years after the Big Bang, light can finally travel. And this light continues to travel today. So it's what we call background radiation from the Big Bang, has been traveling freely across the universe since atoms formed when the universe was 3000 Kelvin. It happened 380,000 years after the Big Bang, and we call it recombination. So the universe goes from being opaque to being transparent. Now, something very important about this, and I hope I have time to, yeah, I do have time. So something very important about this is that this cosmic radiation has been traveling for more than 13 billion years. And you know what happens to light when it travels in an expanding universe. So I wish I had a poll for that. But when light travels in an expanding universe, it gets redshifted. So the wavelength, which would have been like red light a long time ago, has been redshifted to microwaves, right? So it started off somewhere around here, and by now it is microwaves. And here's the bottom line. If the Big Bang theory is correct, then we should be able to see this light that is still traveling. This is, again, this is the leftover from the Big Bang, right? This is when light was finally able to travel. And you should be able to see it everywhere because it was the entire universe that emitted this light. And it has been traveling, again, for more than 13 billion years. And by now it should be in the microwave. So can we see that light? And the answer is yes. This cosmic microwave background, or CMB, was first detected, and it was by chance, by two people, Penzias and Wilson, in 1965. So these two guys were working for AT&T, and what happened is they were looking at some microwave wavelength for communications with AT&T. And they kept hearing this noise, and they couldn't figure out what the source of the noise was. Their job was to get rid of the noise. Finally, they realized that the noise was not coming from Earth. The noise was coming from space. And so they were like, what is this? And then they figured out, they got in touch with some people from Princeton who were physicists who were working on the Big Bang theory. And then they figure out, wow, this is actually the leftover light from the Big Bang, which is now in microwaves. Today, you can still see it. I mean, if you happen to have an old TV set, you know, the kind that is not digital, and you go to a channel that doesn't have a station, and you get this hash, a few % of that hash actually comes from the CMB. So you can use an old TV set to detect the leftover light from the Big Bang. And since then, several satellites have been launched to obtain better measurements of the CMB. So, good, I still have time. All right, so if you were to take a map of the entire sky in every direction, and then you sort of unfold it, this is what it looks like. This is a map of the CMB. Here we've removed stars, we've removed our galaxy so that you can see what it is. This is super high contrast. The difference in intensity between the red and the dark blue is about 10 to the minus 5 in 1, right? Like it's a tiny, tiny difference in percentage. So it's very smooth, but there is some tiny variations. There's tiny variations of temperature. And as it turns out, those tiny variations are responsible for the structure that we see in the universe today. Some of the parts that have lower temperatures had higher densities. And then over time, that's where dark matter accumulated. That's where stars and gas form, and then galaxies form. And so that structure that you see in the CMB is what led to the structure that we see today of galaxies and stars and gas and dark matter and everything that we see. So it's kind of a really cool thing because we could see this CMB and now we can test everything, right? We can put in all the physics and all the astronomy that we know, we put it into models, we take the CMB and then we let it run, and it actually forms the universe like the one that we see today. So the summary of this all, first, we have the Planck era, the dawn of time, right? We don't know anything about the Planck era because we don't have the physics that describe quantum mechanics and general relativity together. But after that, well, we have the Gutt era, over here. So this is when three forces were together, including the strong force. And when the strong force separates, then we have inflation. Inflation is when the universe grows at a very extreme rate. And then after inflation, we get several eras. We only talked about nucleosynthesis. Nucleosynthesis is when the entire universe is like the center of a star, fusing hydrogen into helium. At the end, after nucleosynthesis, after the universe gets cooler, we get recombination, which is when the universe becomes transparent. That happens 380,000 years after the Big Bang. And then after that, then the universe is free to form atoms and then gas and then stars and then galaxies. So then 13.7 billion years later, we get today, we get the universe that we know. So numbers that I want you to learn from this, you don't need to, Planck era is a tiny fraction of a second, 380,000 for recombination, and of course the age of the universe today, which is close to 14 billion years. So that's it. That's the Big Bang in a nutshell. And it was really fun teaching you guys this quarter. It's too bad we weren't in person, but I look forward to seeing you on Wednesday. And I'll stay behind as usual for questions, and hope to see you also on Sunday for the review. So have a great weekend, and I will see you guys later.